In this video we're going to introduce a really important number which is usually denoted by the letter E. So let's have a look at where we've got to so far. In the previous video we discovered that if we had the exponential curve f of x equals 2 to the power x, then the gradient function f dash x was equal to 0.693 times by 2 to the x. We were able to justify this result using algebra, and we noted that 0.693 was in fact the gradient of the curve y equals 2 to the power x at the point where x equals 0, or if you like, it's the value of f dash 0. In addition, if you looked at the challenge question at the end of the previous video, you may also have discovered that if we started off with the function f of x equals 1.5 to the power x, then f dash x turned out to be 0.405 times 1.5 to the power x. And again, you might have been able to justify this result using some algebra. In general, if a is a positive number and f of x equals a to the power x, then the derivative function, the gradient function f dash x, is equal to k times a to the power x, where k is a constant that depends on the value of a and represents the gradient of the curve y equals a to the x at the point where x equals 0, or equivalently, k represents the value of f dash 0. Now this result tells us that for the curve y equals a to the power x, the gradient at any point is proportional to the y value of the point on the curve that we're considering. Unfortunately though, this result is not that much use unless we have a table showing how the value of k varies with the value of a. There is, however, a way round this problem. And what we're going to try and do is we're going to try and find the value of a which has the corresponding value of k equal to 1. And we're going to use GeoGebra to help us do that. So what we're trying to find is we're trying to find the value a as a property that if f of x is a to the power x, then f dash x, the gradient function, is itself 1 times a to the x. In other words, the gradient function is also a to the x. So, looking at our GeoGebra here, we've got the graph at the moment of y equals 2 to the x. So we're looking at the function f of x equals 2 to the x is the red function, and the blue function is our gradient curve for 2 to the x, or the gradient estimate curve for 2 to the x, using a value of h of 0.001. And a little bit of algebra, like the algebra that we did at the end of the previous video, will show us that the equation of the gradient estimate is 0.693 times by 2 to the power x. Now if we start the video off then, at this point, what we're going to do is change the value of a. And as a gets bigger, you can see that the blue curve is getting closer and closer to the red curve. And at 2.6 it's very close, 2.7 it's also very close. 2.8, the gradient curve is now getting bigger than the original curve. So let's now zoom in and take the value of a now to be something between 2.6 and 2.8. And if we take, and we're now going to use increments of 0.01, So for what f of x equals 2.6 to the x, we're less, the gradient estimate is less than the function. But now, as we increase, the gradient estimate is now bigger than the original function. So at this stage we can see that there is a value somewhere between 2.7 and 2.75 for which the two graphs will actually coincide. So at 2.7 it's a little bit less, at 2.71 it's a little bit less, at 2.72 it's a little bit more than the original function. So if we zoom in again, so in this time again for values of a, which are between 2.7 and 2.72, but 2.705 were a bit less, 2.71 were a bit less, 2.715 were a bit less, and at 2.72 the gradient estimate is just a little bit more than the original function. So at this stage we can see that there is a value of a which corrected 2 decimal places is 2.72 with the property that for this value of a, the gradient of the curve y equals a to the x at any point is actually just a to the x. And this number, whose accurate value is somewhere around about 2.7182, is usually denoted by the letter E. So there's a number E which is somewhere around about 2.718 with the important property that if we have y equals e to the x, then the gradient dy by dx is also e to the x. For an example of using this, find the derivative of each of the following functions. Well, if f of x is e to the x minus 4, then we can say that f dash x is going to be the derivative 7 times the derivative of e to the x, and we've just found out the derivative of e to the x is e to the x, minus the derivative of 4, and the derivative of 4 is just 0. So we've got f dash x is 7e to the x. And for part B, if g of x is 2x cubed minus 5e to the x plus 9, we know the derivative of 2x cubed is 6x squared. We know the derivative of 5e to the x is just going to be 5e to the x. We know the derivative of 9 is 0, so we can say that g dash x is going to be 6x squared minus 5e to the x. Now, the next thing I want to do is I want to consider the gradient of the graph f of x is e to the 0.2x. So on the diagram at the moment we have got the curve of y equals e to the 0.2x. Onto this curve we're going to add the gradient estimate curve, again using h equals 0.001. At the point where x equals 0, the gradient of the curve is 0.2. At the point where x equals 1, the gradient is 0.244. The point where x equals 2, the gradient is 0.298. At the point where x equals 3, the gradient is 0.364. And then finally, at the point where x equals 4, the gradient of the curve is 0.445. Now let's take that diagram and look at the results a little bit more carefully. The gradient at the point where x equals 0 is just 0.2 times 1. The gradient at the point where x equals 1 is 0.2 times 1.22. The gradient at the point where x equals 2 is 0.2 times by 1.49. The gradient at the point where x equals 3 is 0.2 times by 1.82. And the gradient of the curve at the point where x equals 4 is 0.2 times by 2.225. In other words, we can see that in each case, the gradient of the curve at a point P is 0.2 times the y value of the point P. We know the curve has equation y equals e to the power of 0.2 times x. So at a general point P with coordinates x, e to the power of 0.2x, the gradient of the curve is going to be 0.2 times by e to the 0.2x. In other words, we've got the gradient rule for f of x equals e to the 0.2x is f dash x equals 0.2 e to the 0.2x. Let's now have a look at a second example. In this case, we'll have a look at the example of trying to find the gradient of f of x equals e to the minus 0.5x. Starting with the curve y equals e to the power of minus 0.5x. Then we add the gradient estimate curve and start looking at the gradient values for particular points. So at the point 0, 1, the gradient is minus 0.5. Where x equals 1, the gradient is minus 0.303. Where x equals 2, the gradient is minus 0.184. Where x equals 3, the gradient is minus 0.112. And where x equals 4, the gradient is minus 0.068. Looking at these results in more detail, the gradient when x equals 0 is just minus 0.5 times 1. The gradient when x equals 1 is minus 0.5 times 0.607 to a reasonable degree of accuracy. When x equals 2, the gradient is minus 0.5 times by 0.368. When x is 3, the gradient is minus 0.5 times by 0.223, with a little bit of rounding being done. And when x is 4, the gradient is minus 0.5 times by 0.135, again with a little bit of rounding going on. So we can see that in each case, the gradient of the curve is minus 0.5 times by the y value of the point under consideration. But we know the curve has got equation y equals minus 0.5x. So for a general point on the curve, we've got the rule that the gradient of the curve is minus 0.5 times by the y value of that particular point on the curve, which is e to the minus 0.5x. So we've got if f of x is e to the minus 0.5x, then the gradient rule is f dash x is minus 0.5 e to the 0.5x. So we've got these two rules from the previous slides. In general, if we've got f of x is e to the kx, then the derivative f dash x, the gradient function f dash x, is k e to the kx. So, for a second example, if we want to find the gradient rule, if we want to find dy by dx if y equals 7e to the 2x minus 5e to the minus 3x, then we've got dy by dx is going to be 7 lots of the gradient of e to the 2x, in other words 7 times 2e to the 2x, minus 5 times the gradient of e to the minus 3x, which is going to be minus 5 times by minus 3 e to the minus 3x, which simplifies to 14e to the 2x plus 15e to the minus 3x. Similarly for part B, dy by dx is going to be 5 times 2x minus 3 times minus e to the minus x plus nothing, because e to the minus x is just the same thing as e to the minus 1x, so the derivative of e to the minus x is going to be minus e to the minus x. Simplifying that expression, we get 10x plus 3e to the minus x. For the next example, we've got to find the value of the gradient function when x equals 2 if the original function is g of x, where g of x equals e to the 3x times by 2 minus 10 e to the minus 2.5x. To answer this, then we need to start by multiplying out the brackets. So we've got g of x can be written as 2e to the 3x minus 10e to the 0.5x, because e to the 3x times e to the minus 2.5x is e to the 3x plus minus 2.5x, in other words e to the 0.5x. Just use your laws of indices carefully. In which case we can say that the gradient rule g dash x is going to be 2 times 3e to the 3x minus 10 times 0.5 e to the 0.5x, which simplifies to 6e to the 3x minus 5e to the 0.5x. So the value of g dash 2 is going to be 6e to the power 6 minus 5e to the power 1, and e to the power 1 is just e. So using our calculator, that gives us a value of approximately 2,407. And for our final example, we've got to find the equation of the tangent to the curve y equals 4e to the 2x plus 3e to the minus 2x add 5 at the point where the curve meets the y-axis. Well, if x equals 0, then the y value is 4e to the 0 plus 3e to the 0 plus 5. E to the 0 is 1, so the y value is simply 12. So the point where the curve meets the y-axis is the point 0 to 12. Differentiating, we've got dy by dx is going to be 4 times 2e to the 2x plus 3 times minus 2e to the minus 2x plus the gradient of 5, and the gradient of 5 is 0. So we've got dy by dx is 8e to the 2x minus 6e to the minus 2x. When x equals 0, we've got dy by dx is 8e to the 0, take away 6e to the 0, so dy by dx is 2. So the tangent is a line of gradient 2 which passes through the point 0, 12, so the equation of the tangent must be y equals 2x plus 12. That concludes our introduction to this really important number e.